to the third part of my talk, the lectures. So it's still under the line of halo nuclei clustering and universality. And so yesterday we talked about universality and how to use effective field theory to describe it, and focus on two-body problems. And today we will mainly focus on three-body problems and see what kind of universality will appear in the three-body in three-body systems. So like what we said yesterday is that in the universal physics means that there are general properties in those weakly bound few body systems that are those properties are model independent. So that can be applied to physics at very different fields. So systems with very different interactions, you can find the similar behavior within those systems. So one type of universal physics can be described by those universal scaling laws. So basically, if you in the three-body system, for example, you can have an observable at a given energy E that can be related to two-body and three-body binding energies in the systems in the scaling law behavior. So this O3 is representing this observable, this three-body observable at given energy E, and so it's written as first of all, it's proportional, scaled with this three-body binding energy with a given dimension. So this dimension is related to the dimension of this observable. And there will be universal functions appear as the ratio between different quantities. So the first quantity is this observable at a given energy E divided by the three-body energies, for example, the ground state energy of the three-body systems. And also it's correlated with the ratio between the two-body binding energy and the three-body over the three-body binding energies. And here this minus and plus sign refers to if your the two-body subsystems has a virtual state or real bound state, right? So the sign will be different. Okay. So then we can, if we want to describe these three-body systems using a general Lagrangian, we can write down this one-line equations. So it's very similar to what we talked yesterday. First of all, it has a single particle kinetic term. So here, remember, we are talking about three identical boson systems. So it's simplified systems. So here you only have, this is like a single boson field. And then if you introduce this two-body dimer field to represent the two-body interactions, so you will have this this dimer field with a residual mass. So here, since we to make it simple, so we just stay at leading orders. There's no kinetic terms coming here. There's only this rest mass, this static term. And the interaction is described by this additional dimer coupled to two single boson fields. So it's a dimer boson field with this G is a two-body coupling constant. And so what's more in this for the three-body system is that you have an additional term coming in that is described by a dimer coupled with single bosons. So it's actually looks like this diagrams on the bottoms. So you have an incoming boson couples with the dimer field, then at this point, then it goes back to a single boson and the dimer field. So so this is representing a three-body force in your systems. So the general way of solving this is that for two-body systems, you can solve the Klipman-Schwinger equations as we talked yesterday, and use that to calculate the T matrix and reproduce parameters in the T matrix. So at leading order, this parameter can be related to the scattering length. And you can tune this two-body coupling constant to fit to the scattering length. So then your two-body interaction is determined, right? So then you move to the three-body systems to solve this three-body equation. So this can be, in quantum mechanics, it's related to the Faddeev equations. And I'll go to details about how to calculate these equations later. So, but just to briefly mention that this bubble here representing a three-body scattering amplitude, which is written as a single particle scattering with a dimer field. So then it goes back to a dimer and a single particle. So you can solve this boson-dimer scattering amplitude with these Feynman diagrams. I will explain why this is looking like this in the later slides. But then you have this three-body coupling coming in, which is related to this coupling constant H. Then this needs to be tuned to reproduce a three-body observables in your systems. So then your prediction of this T matrix and other observables can be model independent or cutoff independent. Okay. So that's the general idea of how to do this. And so then there's an interesting effect in the three-body systems that is called the Thomas Efimov effect. So it was first discovered by Thomas that he found that if you fix the two-body binding energies in your systems, suppose you have just a square well potential for your two-body system, right? So you can tune the depths of your potentials and fix your two-body binding energies. But then if you change your interaction range from a finite range to zero range, so the range go to zero, or in the momentum space, we will call it a cutoff go to infinities, then you find a very strange behavior is that although this two-body binding energy is fixed, the three-body binding energy calculated at the limits L go to zero will blows up, go to infinities, which means that if you have a zero range, then this three-body system will collapse into a single point. So this is called the Thomas collapse, and this is shown by this plot here. Well, this is calculated in momentum space. So basically, once your cutoff go to infinities, and the red line is representing the ground state. So the ground state binding energies, three-body binding energies, will then just blows up, go to infinities. So this is what people call the Thomas collapse. And later on, Efimov, I think it was in 1970s, so he explained this three-body behavior in a different way. So he is saying that, okay, so if the range goes to zeros, the system collapses. So now we fix the range, right? So you fix the interaction range, but tune your two-body potentials that to make the two-body binding energy go to zero. So it's a different way, right? So now the two-body binding energy go to zero, and in other way we are calling this scattering length go to infinity. So this is called the unitary limit. And if you go back to this plot, it means that so now the number, the cutoff is a fixed number, it's a finite number, but when the two-body binding energy go to zero, this ratio still go to infinities, right? So the denominator go to zero, this thing go to infinity. So suppose what you calculate for the three-body binding ground state three-body binding energy is finite, but if you look at the ratio, things so B30 is finite, but B2 go to zeros. This ratio still goes to infinities. So, but the interesting is that if you keep the two-body binding energies, so in this plot it means that we're plotting lambda as a function of B2. So if B2 go to zeros, lambda will still keep going up in this directions. So then when B2 is keep reducing, you have not just one ground state or one bound state, but then at a certain point there will emerge another bound state, right? An excited bound state. And if you keep reducing the two-body binding energies, more three-body bound states will then appear. So it appears as a geometric towers. This is related to the discrete scaling symmetries in three-body systems. And this was found by Efimov at that time. So actually, if we can use this same plot to explain both the Thomas collapse and the Efimov effect. And they are actually it's like the two sides of the same coin. It depends on how you explain this, right? So both of these cases, those cases are related to the limit L over A go to infinity. It's the first case, Thomas collapse, L go to zero. The second case, Efimov effect, A go to infinities. So you can use the same plot to understand Thomas effects, Thomas collapse and Efimov effects. And for those effects, it reveals some interesting symmetries or scaling laws in the three-body systems. And it shows both continuous scaling symmetries and discrete scaling symmetries in these three-body systems. Okay, so then to in the calculations, if you want to prevent the system to collapse when L go to zeros, what you can do is you can introduce a three-body force in the systems. So once you introduce this three-body force, you can fix the ground state binding energies, and then what you need to do is you tune your three-body force according to this these cutoff parameters, or let's say according to this interaction range L. So this has been done in the let's say the effective field theory framework, and it was plotted for this three-body force. So this H lambda is a function of the coupling. We talk about this coupling constant H for atom-dimer interactions at the couple of slides earlier. So they find that once you increase the cutoffs, this three-body force will have this log oscillation behaviors. It means that it blows up at a certain point, then it appear from minus infinities to plus infinities, and then would have this log oscillations and will keep going. So this is actually called the RG limit cycles. So which means that it has a periodic behaviors. So what you can also find is that once you tune your three-body force, you can fix the one three-body observables in your systems. For example, the binding energies of the three-body systems, and then the system, the ground state binding energy will be fixed at certain one number, right? It's not changed anymore. So then you will predict the excited states and the first excited states and the second excited states. They will appear the discrete scaling symmetries, right? It's a geometric towers, but the ground state is already fixed. So it's not a continuous symmetry anymore. It becomes this discrete. The only left is this discrete scaling symmetries.
Excuse me, can I ask? This is quite interesting. In the case three-body force, that is a phenomenological parameter. You mean what is the origin for the three-body force? That means that in order to avoid the Thomas collapse, just introduce this term phenomenologically. Is this so? This is repulsive.
It can be both repulsive or attractive. It's not it's not phenomenological. It's just you introduce these three-body interactions in your Hamiltonian, in your Lagrangians, but then what we call this is a renormalization process. So you need to want to make sure your prediction is independent of these cutoff parameters.
I see. So because so sometimes I try to calculate the helium-4 and bosonic system and just call atomic system, and in this case we have some realistic interaction, but we have a very high core. So then if we include the two-body level with a high core, then I don't need to have such kind. We never encountered this Thomas collapse and effect due to the repulsive term for the two-body system. So sometimes I'm confused. So in this case, two-body system potential is like a delta function. Is also attractive.
So this is a leading order calculation. So this is like a how do I say this? So if you stay at a certain cutoffs, it doesn't collapse into infinities, right? So for example, if we just keep your cutoff low at around here, this binding energy, three-body binding energy will stay at the finite numbers. So then you can look at the corresponding plot for this three-body force. If your cutoff is around here, this three-body force is really weak. You can suppress it to be close to zeros.
I see.
But if you're moving away from that, if you keep your cutoff get to larger and larger, or the range goes smaller and smaller, then this three-body force is really getting strong. It's needed to push this binding energy down to a certain number.
Okay, so then let me understand. So that means Thomas collapse is dependent on the cutoff mass, And if the so
Yeah.
just a short range interaction is so the how do I say it's a so shorter range, then it's just almost Thomas collapse. It sometimes happen.
Yeah,
But
and
if
at
we
certain
have some
point,
smeared.
if you make this range go to smaller and smaller, it will certainly at some
Okay,
point will
like a
happen.
delta function.
Right.
Okay,
At
that
the
I
delta
understand.
function. Yeah, yes. Okay, so well, what happens after you renormalize this system is that because this three-body force will have this log oscillation behaviors, it means that if you change the interaction range by a factor of this 22.7, your three-body force will be the same, right? The system will have the same three-body interactions. So it will also tell you that your systems, when you rescale your system, the size of the system will change, make it larger by this factor 22.7, or make it smaller by the same factors. The system will have the same interaction and will have the same behavior. And this was found in the around 2000, I think around 2000 in the ultra cold atomic gases. So they find this behavior that the system will have this Efimov effect behaviors. And so this is actually a plot for this three-body binding energies versus the two-body scattering lengths. And so if you follow this line, you will see that on the, so you can take this as the y-axis. So if you are staying on the left-hand side, this two-body system will have a negative scattering length, which means that the two-body system is unbound. But the scattering length is quite large, so it's from a virtual state. Okay, so if you keep moving from here and to the right-hand side, the two-body system will have a positive scattering length. So it's a shallow bound state. And then, but the three-body system will also have a bound state. So the binding energy change with the scattering length in this way. And so if you are close to the unitary limit, which means A go to either minus infinity or positive infinities, it appears a geometric tower of bound state. So it means your ground state here, so with a factor 22.7 squared divided by 22.7 squared, you will find an excited state. And if you divide by the same factors, you will find the second excited state and the third excited state, one above the other. Okay, so that's well, that's not just the only fact that people discover in the ultra-cold atoms. They can change apply an external magnetic field to the systems and vary the cold atoms near a Feshbach resonance. So the scattering length can change along this line from minus numbers to positive numbers. So they can just track the three-body binding energies along these lines. And if you are close to here, what happens is that the three-body system is nearly bounded. The binding energy is zero. So the three atoms at very low energies or very low temperatures will happen to just sitting to each other and then collapse into a three-body bound state. And if you are around here, so this line representing, because here you have a two-body bound state, so this is the two-body bound state threshold. So if you above here, you have atom and the dimer two bodies continuum states, but below here, you have a three-body bound state. So if you follow this line here, there will be a resonance between this atom dimer scattering state and the three-body bound states that's happening here. And so those can be actually measured in the experiment. And there's another thing that can be measured in the experiment is along this zero energy lines, which above here you have three free atoms. So what happens is that in this system, it's ultra cold systems. It's trapped by an optical trap, and once at a certain point, once these three atoms meet with each other, they can form into this atom dimer scattering state. So first they are free, right? So then at a certain point when they have a chance to form a dimer and the free atoms, because at the beginning it's energy zeros. So here this dimer has a negative energies. So the system must release some of the energies from this system. And the energy release is given by these free atoms. Okay, so what happens is that you have this system, when it additional kinetic energies, because the temperature is very low. So because of statistics, it's an unstable state. So it will be evaporated from this cold atomic gases. What you can observe is that the density of your ultra cold atomic gases is getting lower. So what they measured is this atomic, what's called the atomic, the loss rate of this atomic gases. So then can determine the position of where this atom dimer resonating with the free atoms happens. So what they found is that they can plot this loss rate of free atoms in the ultra cold atomic gases as a function of the scattering length. And what they find is that there is a certain point, basically it's keep growing when the scattering lengths go to infinities. But there is some dip here. It's representing a recombination minimum. And the position of those minimums are scaled with each other by this same factor, 22.7. So this was observed by different atomic gases, and some of them was published in Nature, and it was a big. I think that at that time, this is a proof of Efimov physics, and everybody was very happy about these findings. Okay. So then let's go to the Efimov physics. Not just happens in ultra cold atoms, but it also happens in the normal atoms. Let's take helium-4 atom example. It has a ground state. So first of all, the two helium atoms can have a dimer, can form into a two-body bond state called a dimer. So its average length is about 0.5 nanometers. So if you compare this with the O3 ozone, right? So this it's actually the two-body scattering length, or the two-body average size is larger than that. And if you put one more atom to this system, it will form into a three-body bond state. And this atom radius to this dimer is about 1.5 nanometers, but it's about the same scale. But what is interesting is that beside this ground state, it also has an excited state. And this excited state has an extremely large size. So you can see from this plot that this atom, the distance from this atom to this two-atom dimer is about 15 nanometers. So the size changed by a factor of 10. And this is actually can be explained in the Efimov plot, that was understand this excited helium trimer as an Efimov state. Okay, and so we can actually, from this plot is an explanation of why this helium trimer state is related to Efimov physics. So it's actually a plot of this three-body binding energies as a function of 1 over the scattering length. And for ultra-cold atoms, because we can apply this magnetic field and varies scattering lengths from minus infinity to plus infinities. But for helium atoms, this scattering length is given by nature. So you cannot change it. It's a fixed numbers. So what you can compare this to Efimov physics is that you draw a vertical line, find where its two-body scattering length is at. So then you will locate where the ground state is at along this Efimov binding energy lines, and also find its excited state. This excited state is very close to this atom diameter threshold, so it's nearly bounded at the three-body systems. And if you put additional energy to it, it's separated into a dimer and an atom. Okay. So besides atomic systems, Efimov physics can also happen in the few nucleon systems. And we talk about this, the Phillips line and Thun line yesterday, and also Ingo mentioned this today. So I think I will just skip the details. Just mention that here you have three-body and three-body correlations, and for the Thun line, then you can find the three-body and four-body correlations, and it can be explained by the simple universal features. Okay, but if you want to use the FMR physics to understand the few nucleon systems, you can also try to put the deuteron and triton on this FMR plot. It's similar to the helium trimers. Here, the nucleon-nucleon interaction is also given by nature, so you cannot change it. So the scattering length is also fixed. So what you can do is you find on this FMR plot where the two-body scattering length is at. So this is given by this vertical line written here. So then you will locate the deuteron. It will have a bound state, so it's actually along this dimer line. And the triton will have an three-body bound state that will be around this this trimer lines. So what you can find for the nuclear system is that because this scattering length is not very large, it's normally relatively small. So 1 over a, this quantity is actually not close to the unitary limit. So if you try, if nature gives us a larger scattering length for deuterons, this line, this vertical line can keep moving to the left. Then you will find not just the the ground state, but then you can find an excited state. But unfortunately, the deuteron scattering length is relatively small, so we are actually along here. So you can only find a ground state, but if you go up, you will find you just hit this dimer threshold, and the next excited state is above this line, so you cannot find an excited triton state in nature. Okay, so but in nuclear physics, we do not just have few nucleon systems, we also have this halo nuclei. And actually, halo nuclei provide more possibility to study this FMR physics, because in these systems you have more possibilities, right? So you have not only the Borromean systems with scattering lengths with a minor scattering length, but you also have those non-Borromean three-body systems where the scattering length is positive. And besides that, besides the S-wave two neutron halos, you also have two neutron halos with P-wave neutron core interactions. And also, you will have two proton halos and four neutron halos that you can have more possibilities to study those few-body universalities and find whether, in some cases, you can find behavior similar to the FMR physics. So that's why we're interested in the halo nuclei. Okay, so now let's talk about how to really solve a three-body problems, and let's focus on the bound state problems. So first of all, you need to write down a Schrodinger equation for the three-body bound state problems. So for simplicity, we just consider two-body interactions here. So don't neglect three-body interactions. So this Hamiltonian is written by this kinetic part. Each particle will have its own kinetic term, and you need to minus the kinetic term of the central mass motion. So this is representing the central mass is moving. So you need to subtract this part out, plus the pairwise interactions as 1, 2, 3 particles. So you have 3 interactions here. So this is the Hamiltonian. When you solve this, this is the three-body wave functions. You get the three-body eigenstate and eigenenergies. So then, because we already moved away the center mass motion, so we moved away the degrees of freedom of the center mass, so you left with 6 dimensions. So the best way to describe it is in the Jacobi coordinates. So in these coordinates, you first of all, so here we write this in momentum space. So first of all, you have a relative momentum between these 2 particles. That's called a pair of particles. So you have their relative momentums. And you start from the center mass of this pair to the third particles, and we normally, in the Faddeev equation, we call this a spectator. So this is watching this pair. And so this momentum representing the relative momentum between the spectator and the center mass of this pair. Okay, so now you defined these 2 momentum that will give you 6 degrees of freedoms. Okay. But in these Jacobi pictures, you not only have one representations. Because you have 1, 2, 3, right? They can form a cyclic permutations. For example, you can have 1, 2 forms into a pair, and then go to 3. 3 is a spectator. But you can also have 2 and 3 forms in a pair, and go to particle 1. So now here, particle 1 is a spectator. And the other way is that you can have 3 and 1 forming a pair and go to particle 2. So particle 2 is now a spectator. So you actually have 3 different representations in this Jacobi coordinates. Okay, so according to these 3 different representations, you can separate your 3-body wave functions into 3 components. So this is called Faddeev components. So then you can, these Faddeev components can be written in this way, so it will satisfy this separated Schrödinger equations. So you can understand this by your free Hamiltonians plus 3 interactions. So now you need to sum also the 3 Faddeev components. So this will go to E times these 3 Faddeev components. Okay, so by this separation, we can write this into 3 equations. So first of all, you will have, so you can write I as a, so let me change here. So this is I, right? This is I, right? So you separate the I component from these equations and put the H0 to the right-hand side. You have Vi times this whole thing and equals E minus H0. And you pick the I component from here, so you have psi I. And now here, this I can be 1, 2, and 3, and here you still have a summation of all the Faddeev components. So it's actually coupled channel equations, 3 equations coupled with each other. Okay, so in this, if we use the spectator representations, we can now simplify this 2-body interactions as V1, representing the particle 1 is spectator, and actually V1 describe the 2-body interactions between particle 2 and 3, and this V2 represent the 2-body interactions between 3 and 1, and such and such. Okay, so now start from this line, you can divide this E minus H0 back to the left-hand side, so it will give you a Green's function G0 here. And just to remember that here this the summation of psi 1, psi 2, and psi 3 also include this psi I components. So you separate that part out, you will have this 1 minus G0 Vi psi I equals to G0 Vi times the left components, so that would be the component not equal to I. Okay, so then the next thing is that you divide this operator in this bracket back to the right. So now you have psi I equals 1 minus G0 Vi to the power. Well, so it's actually inverse, right? It's an operator. It's not just U1 divided by a number. It's actually, you can think about this as an operator inverse. Okay, so we can talk about how to calculate this in the next slides. Okay, so basically you write this will be a derived Faddeev equations in this form. Okay, so then let's look at these equations, and it includes 2-body interactions, and also the 3-body Green's functions, and also the Faddeev component for 3-body wave functions. So then the next thing is that you can use the solutions for the 2-body problems to simplify these equations. So if you remember from the talk in the yesterday, is that we can write down Lippmann-Schwinger equations to relate the 2-body interactions to the 2-body T matrix. So this is normally written as T equals V plus V G0T. Okay, this is representing a 2-body system. So here, this notation might be a little bit confusing. So Ti means, so if you have T1, it actually means the T matrix for particle 2 and 3. And also V1 means the pair interaction for particle 2 and 3. Okay, so it's representing the two-body subsystems. So you have this T matrix for the two-body subsystems. Okay, but then you need to embed this into three-body system, right? So it's not just two-body in its own center of mass anymore. It's in the three-body center of mass system anymore. So three-body center of mass systems now. So now this T matrix has its two-body relative momentums, and its energy is the two-body relative energy is related to three-body energies minus the relative energy between the spectator and the pair. You can think about the whole system's energy is written as energies between the pairs. Let's say. So E is representing the three-body energy for the three-body systems. So you can have the energies between particle and 2 and 3 plus energy 1. The energies between particle 1 and 2 and 3. Right. So this will give you kinetic energy, relative kinetic energies written in the last part as Qi. As I mentioned before, it's representing the relative momentum between particle I and the other pair. And this is a reduced mass. It's representing the reduced mass between the spectator and the pair. So this is, you subtract this kinetic energy out. The left energy is related to the two-body pair interactions. Okay, and the Green's function is also in the three-body forms. So here, you can think about this is actually equivalent to the two-body Green's function, is that you subtract out this spectator, the energy between the spectator and the pair, and the left energy is related to the two-body subsystems. So then you subtract out the relative kinetic energy of the two-body subsystems, you will have this Green's function form, right? So this form can be used for either two-body system and three-body systems. So it doesn't matter. It just contains all the Jacobi momentums. Okay, so now here let's look at what we have before. Is that we have this ugly term in the front of this Faddeev equations. So then we try to make it simple. So you put this out, and once you expand this, it will turn into 1 plus G0 Vi, and this thing squared plus infinity terms. So this will be similar to if you do 1 minus x, it becomes 1 plus x squared plus many other powers terms. So if you recombine this, pull one G0 to the left, we're left with Vi, G0, Vi, and other higher powers terms. And this whole thing actually would be exactly the same as the T matrix. So this whole quantity will end up with a G0 times T times this two-body T matrix. So you absorb all the information of these two-body interactions into this T matrix. This, in the end, your Faddeev equation would looks much simpler. It would be related to the Faddeev components and also the two-body T matrix times the Green's function. So what we need to solve is these equations. Okay, all the two-body information is already embedded in the two-body T matrix. Okay, and so to follow any explanations, let's still focus on system with 3 identical bosons. So in this case, the 3 Faddeev components, because you have 3 identical bosons, the 3 Faddeev components will be the same, right? So the behavior will be exactly the same. So you can pick just one component, psi I, and the other pieces will be written as the permutations with this psi I. So you just need to do a permutation because they're the same particles, right? You just need to permutate your coordinates will be related to the other Faddeev components. So this is what this permutation operator will do. It will do this cyclic permutation from one representation to the other 2 representations. Okay. So actually, there are many literatures about how to solve these Faddeev equations. So two examples is the one by Hefnan and Thomas, and this is the book by Glocko. So you can read those to understand how to solve Faddeev equations. But I decided not to follow the rigorous way of explain how to do these calculations, because we can actually use effective field theories and draw Feynman diagrams. It's actually have the same meaning as these Faddeev equations. So here, let's look at this equation. So here you have an amplitude representing the atom dimer, this atom dimer combined into a three-body systems. So it's a transition between atom dimer states to a three-body systems, which is similar to this Faddeev component because you pick one particle as the spectators. Okay, so and then on the left-hand side, you have, so here, if you look at this part, it's actually a Green's function because you have a single particle line here. So this part is actually the same as a Green's function. And this dimer field is similar as this two-body T matrix. Because we mentioned yesterday that it's a dimer propagator. It's in the end, once you project into the momentum space, it's related to this two-body T matrix. And this line here representing you just change from one spectator frame to the other spectator frame, because here you have this particle as the spectator interacting with the pair, but once you exchange the particles, you have this particle exchange, a different particle will be the spectator, right? So the pair will be a different pair. So this particle exchange between two dimers is exactly the same as these permutation operators. So these Feynman diagrams have the same meaning as these Faddeev equations. So now we can just use these Feynman diagrams to solve the problems, and you will get the same answer as solving Faddeev equations. Okay, so how to solve this? This equation is then normally we call this as ST. So you solve this amplitude for, so let's take bound state and examples. This amplitude is related to the three-body binding energies, and there is a momentum Q between between this boson and the dimer field. So then for this loop diagrams, particle exchange loop diagrams, so you will have two single particle field, single particle propagators, IS representing this line here, and another one representing this particle exchange line here. And also in this loop, you will have this dimer propagators. This will be this ID zeros, and you will have another amplitude that will be this IAN. So actually, it's just IA. And so what you need to make sure is that you need to keep the momentum conservations in between this when you do this particle exchange. So for example, here you start with Q. This particle has a momentum Q, right? So it's the same. This particle has a momentum Q. Then the dimer has momentum minus Q. So then once you do particle exchange, this line here, this single particle line, will have a momentum minus Q prime. So it carries a momentum minus Q prime. Then what's left with this single line is that it has a momentum Q prime. When you add these two, it has momentum Q minus Q prime, right? So this is, you keep the momentum conservation inside this loop. So then what you can do is you have this four-dimensional integrals. You pick out the Q0 prime integrals. So they use the Cauchy residue theorems. You can just remove one single line, one single particle propagators. This will end up with a form for solve. It looks like an integral equations. So here, the thing in this denominator is representing the dimer field. Actually, it's the S-wave dimer field. And so then you have this part will turn into a Green's function. But because you have here, you have Q plus Q prime, so there will be angle between these two. So once you put this thing squared, it will turn into an angle between. So here this X is representing the angle between Q and Q prime. So you need to solve this in a three-dimensional equations. Okay, so then what you need to do is that because we're solving S-wave problems, it means that not only the dimer is in S-wave, but the whole three-body system is in S-wave. So then you need to project your the amplitude to S-wave only, so the whole system to S-wave. So after you do that, it's in tune into a new equation. So here, this M function, its kernel function, is by projecting the Green's function to S-wave, so you end up with this new form. So if you solve this, you will get the binding energies of the three-body systems. And what you need to do is here you need to add the three-body force for regularization, for renormalization purpose, because now you need to put a cutoff to this momentum integrals. So here you reduce from three-dimensionals to one-dimensional, right? Because you integrate out the angles parts using S-wave projections. Okay, so after that, you will find that your integral equations has scaling symmetries, because if you look at when this Q goes to really large numbers, you can neglect the binding energies and the two-body binding energies and the three-body binding energies in the systems. Gamma 0 and B3 can be neglected. Then this equation will look like this. Here it's like this amplitude A, and we can put this amplitude A to have asymptotic behaviors. So you assign an arbitrary power to it, and for the final answers, we just, it's like a little bit cheating that you will know that the power is a complex numbers. So it's actually looking like an imaginary part minus a real part. So you can put it with some powers, and then you will realize that if you divide this thing back to here, this will turn to a scaling between Q prime and Q, and this equation will be just a dimensionless equation, integral equations. Everything is written in a scaling factors, Q prime over Q. So this equations, normally we call it a Mailing transform, has a solution for this S0s. This is in three-body system. I think normally they call it a transcendental equations. It's exactly the same if you solve it in coordinate space using hyperspherical formalisms. Okay, so its solution is that this S0 is 1.00624. It's a given now. It's a number that can be solved from these equations, or you can just plot it, right? So you can find where it crosses this one, and then you find the numbers. So then it finds that because you have plus I S0 and minus I0, so you combine these two, you get this asymptotic behavior of the amplitude as cosine S0 log Q over some scale. So this is like a phase shift, right? So you have, basically you start with C plus Q I S0 minus 1 plus C minus Q minus IS0 minus 1. And if you combine these two, you will have the relation between these two coefficients will give you a phase shift, right? Additional phase. And this phase can be written in this lambda star form. Okay, so you will find that your this three-body amplitude has a scaling symmetry, is that if you scale your Q, momentum Q by this additional factor, e to the pi over S0, which is just 22.7, this you just need to rescale your amplitude by the same factor, divide by the same factor, then you end up with the same STM equations. The equation doesn't change, which means your physics does not change after you do the rescaling. Okay, so the other thing we need to do is that once you introduce the three-body force, you need to make sure your three-body, the STM equation is still cutoff independent, is that you have to tune your three-body force, make sure that when lambda go to large numbers, you integrate this thing, and it will turn to 0 because to cancel all the cutoff dependence. So if you solve this, you have the analytic form for your three-body force as a function of the cutoff. And here, again, here this lambda star is the phase we showed before, and it actually turns into a three-body parameters. So these parameters can be related to a real three-body observables. For example, the ground state binding energies on your systems. So this can be then determined by some fit to physical systems. Okay, and if you plot this function, it just looks like what we talked before, that it has this log oscillation behaviors related to limit cycles. So then it has this STM equation has a discrete scaling symmetries, which means that if you change everything by the same factors, Q go to Q times 22.7, and two-body binding energies go to the same factors, and three-body binding energies to 22.7 squared, your STM equation stays exactly the same, and it means the physics you will find for your system will stay the same. So this is actually what we call the discrete scaling symmetries. Okay, so and this actually works if you have a really large scattering length. So the interaction range over A is much smaller than 1. So you will find this geometric spectrum, three-body binding energies versus 1 over A, plotted as the geometric spectrums. And this three-body parameters, lambda star, need to be renormalized, right? It need to be turned into one, for example, the ground state binding energies, then the other state will be determined. Okay, and in reality, this interaction range is related to the 1 over the cutoff, and it characterizes the range of applicability of the universal physics. So you can draw a circle representing the radius of 1 over r. The physics you can describe must be sit inside these circles. Okay, yeah, questions?
Can you in principle also choose other regularizations, such as
Yes, yes. You can choose, so here I show the example of hard cutoff, but you can choose Gaussian regulators and others. You will observe the same behaviors, yeah. Yeah, actually, once your cutoff goes to very large numbers, this doesn't matter. It's the same. It's almost the same. But what will happen is that once you can understand from this plot that if you are varying your three-body force and make sure the three-body ground state will fix to a certain numbers, but if your circle keeps growing, it will certainly at some point will hit another bound state, right? It will hit a deeper bound state. So this actually happens in this rounding of the three-body cutoff. If you go from one branch, when it goes to infinities, it means that at this point, you try your best to tune the three-body force to make sure the ground state will go to the real binding energies, but it doesn't work anymore because it's already infinities. So once you jump to another branch, you need to fit the excited state to the physical values, and you will have inevitably have a deeper ground state sitting in your systems. So this is what happens in the three-body pictures. So it will apply a bigger range, or applicable range for your descriptions. Okay, and so this is an explanation of why you can see this ephemeral physics in three identical bosons. But now let's move to the systems, three-body systems with two neutron halos. So here, for this two neutron halo systems, we have two neutron and the core forming a three-body systems. And the way to calculate it is similar to the three identical bosons, but the difference is that now you have two different amplitudes, AC and AN. AC representing the transition from a core and the dimer, two neutron dimer field to the ground state, to the bound state, and AN representing the transition from a neutron and the neutron core dimer field to this bound state. And it's also written in this using particle exchange. You can write down in this coupled channel in Faddeev equations, or we call it integral equations. Okay, so just from then you solve this by using Feynman diagrams. So you turn it into coupled channel integral equations. I think I don't need to give too much details and just mention that here you have different Green's functions related to using different spectators. So here is a spectator with neutron as a spectator. Here GC is using the core as a spectator. So you write down, and here you have some coefficients related to the mass ratio, right? Reduced mass will be different using different spectators because now you don't have identical particles. You have a core which has a mass A and two neutrons which have mass 1. So if you change from one spectator to the other spectator, the reduced mass will be changed. So this is you can use some geometry or just use momentum conservation, energy conservation to figure this out. And here is some momentum defined as a combination. When you tell you how to do this change from one frame to the other. Okay. So now in this part you have two-body T matrix. One is related to this neutron-neutron S matrix, and the other one is S-wave T matrix. The other one is related to this neutron core S-wave T matrix. You have to plug these two in. And to obtain a two neutron halos in total S-wave, we need to perform an S-wave projection. Also, again, S-wave projection to these integral equations. So after doing that, you end up with these new equations where this X function is related to by projecting the Green's function to its S-wave. So you just solve these equations, and then you can obtain the binding energies from these integral equations. So what we find is that you need to tune your three-body force as a function of the cutoff, and then you can fix the binding energy of your systems. So here we did is that we fixed the three-body binding energy to a certain numbers and change the mass ratio. So suppose your core would be different particles. So for A equals 1, which means you have a triton in your system, the three-body systems, and A equals 9, you have a lithium 11, right? 2 neutron and lithium 9 core. And then here you also have carbon 22 and calcium 62. So then you find that for all those systems, it has this limit cycle behavior. Three-body force is log oscillating with this cutoff lambda, but the period of this oscillation which slightly change with the mass ratio. Okay, so it means that the three-body system also has a limit cycle behavior. So it's possible that you might find discrete scaling symmetries in two neutron halos. So it means that we can try to search if there is a possible excited F-mode states in the systems. Okay, so this is what we are trying to find if there is an excited F-mode state. As we mentioned before that, so this is 1 over A, a scattering length, and you have if A is positive, you have a dimer threshold, right? Two-body is bound, so the F-mode plot looks like this. The three-body energies, if A is smaller than zeros, the three-body binding energies will just need to be below 0, so it's a bound state. But if it's on this side, the three-body binding energies need to be smaller than the, oh, well, actually, it's the other way. It will be larger than the two-body binding energy, so you need to below this line here. So you can try to find the limits where you have an excited state. So you can put the excited states exactly at this threshold. And trying to move your two-body scattering length and trying to find where the three-body bound state energy you're finding, right? So this is what we plotted as a contour plot. And on the y-axis is, so you fix the three-body binding energies as the maximum of these three numbers, because if you are if this one neutron separation energy is a positive numbers, so you must stay below this line. So your maximum, the excited states must be at most, at least here, right? So then it will be we will choose the maximum of these three combination numbers. Okay, so then we plot this the function of one neutron separation energy over the two neutron separation. So this is the one neutron separation energy for neutron core, and this is the two neutron separation energy for these two neutron halos. And on the y-axis, you have neutron-neutron energies over the two neutron separation energies. And because in nature that the two neutron has a virtual state, so it's neutron-neutron energy is always negative, so you'll find all the physical observables on the left-hand side of this contour plot. But for the neutron core interactions, you have virtual states and also bound states. So you'll find these two different observables are either on the upper panels or in the bottom panels. So if there exists an excited F-MOF state, then its ground state must be sitting within this contour plot. So it might be sitting inside these regions. But unfortunately, if we compare with all the experimental data, you'll find that most of them are sitting outside these contour regions. So which means it's really difficult to find an excited F-MOF F-MOF states in nature. So this is what we discovered, right? So, but there is one example is this Kelsen 62. It's not an experimental result. It's calculated, I think it was calculated using couple cluster method. But you can combine this with, using this data combined with EFT and realize that at least at this point, this is not ruled out. So maybe future with more accurate results, this might be ruled out. Okay, any questions to this? I mean, this plot is a little bit complicated, but if you have questions, you can feel free to ask. Okay, yes.
You know, like the plot on the left side,
Mm-hmm.
like you start like tracing like the first, like the diagonal one, you know, like the one with the 1/a. Like you start tracing like this diagonal stuff, and then how do you get like the curve like at the bottom, like
On the bottom.
Yeah.
So this is your. If there is an excited state, the ground state must be sitting below it, right? So you need to draw this line here. The ground state must be here.
Okay.
If you move a bit further, scattering length go to smaller, so 1/a, right? So if scattering length is smaller, you're moving to here, means three-body binding energy is larger, then you don't have an excited state anymore.
Okay. Okay. And what about the shape? You know, like
This shape?
yeah. Where does that come from?
This is just you calculate the three-body binding energy versus two-body binding energy.
Okay.
You get this FML plot. Yeah.
Okay.
This is what you can
Okay.
calculate from the FML physics. But then this will provide two thresholds, right? So if two-body system, this region is the Borromean systems, and here you have the non-Borromean system, right? So and in this part, the excited state must be below this threshold, and on the other side, the excited state must be just below zero. Right?
Okay.
So then you just try to find where the ground state energy is at. And if your ground state energy is, let's say, within these regions, means increase two neutron separation energy, make it smaller, right? So they will go inside this plot. And this will help you to find this excited states. But if it goes out, then you cannot find the excited states. That's this plot. What this plot means. Okay, I think I have 5 minutes.
Just remind about that plot. I mean, if you could put, for example, the trimer of the ground state trimer of atomic trimer of helium-3, of helium-4,
Right.
is just inside that curve.
Yeah.
I mean, in atomic physics, we can find examples. Just I want to add.
That's a good point. Yes. Okay, so let me wrap it up. And so here you can also calculate the wave functions using these Feynman diagrams. So you connect this amplitude with outside this free, this three body, three independent particles, and there's a dimer. So you just put this into equations, you would calculate the three-body wave functions in Jacobi coordinates. And then you can use the wave function to calculate this one-body matter density form factors. And you expand the density form factors in low transfer momentum k, you get the radius. You get, for this case, you get the radius between neutron and the neutron core pair. You also have the distance between the core and the neutron pair. So this will help you to reconstruct the matter radius and the charge radius. So you can use that to make some examination of, for example, carbon 22 systems, and this is the measurements what have been done for this carbon 20 to 21, 22. The neutron separation energies for this system is actually not well known. So you can look at here that the carbon 20 is well bound, so this number doesn't change from atomic mass evaluation in 2012 to 2020. But for carbon 21 and carbon 22, this number changed a lot. For example, this is reaction measurements at MSU that they find its neutron separation energy is -1 means it's unbound systems. So it must be smaller than 2.9, which means it has a small scattering length. But for atomic mass evaluations, this number is much smaller. And for these two neutron separation energies in carbon 22, this number also change a lot from time to time. But we can see it's actually still, we understand it's a small number, so it's a really weakly bound systems. It's probably the most weakly bound two neutron halos in the nature. But what we know more accurately is its radius, the matter radius for carbon 20 and carbon 22. So actually, you can use EFT to make correlations between these observables. So you can use the more accurate measurements from the radius to put constraints on the one neutron and two neutron separation energies. So that we can do this, you can find this. So this will be your input, the radius measured from the nature, and it will be turned into correlation functions. So it will turn into correlation between two neutron separation energy and the neutron core separation energies. So we use this as an input, so this will be the central value and the minus plus line representing as this blue and green and the red line here. This will give you the correlation between two neutron separation energy and the neutron core energies. But we did this as only a leading order calculation. So if you estimate the next leading order corrections, it would turn into this band. Okay, so now let's look at how this will compare with the measurements on these neutron separation energies. This is the result from atomic mass evaluation in 2012, and this is the MSU determination of neutron core scattering length. So you will put this black box here. It seems like consistent with what the EFT correlation will predict. But now if you move to 2020, it will show the atomic mass evaluation. If you use these two values, both from AME, so you get this square here, around here. But it's a little bit far away from the central value. I think it will have a high sigma discrepancy, right? But if you combine two neutron separation energies from AME and this and neutron core energies from MSU, early MSU measurements, you have this yellow band here. It's a little bit shift away from the previous results, but would be somehow consistent. Will tell you that it's still possible that you can find the really shallow two neutron halos. But what we also find is that this plot will put an upper limit for this two neutron separation energy will be at most 400 keVs. This is the most, I think that it's the largest value that's possible. Okay. Okay, so then about P-wave interactions. Let's move to helium-6. And this is the 2 neutron halos. What is different from S wave is that the neutron alpha has a p wave interactions. It has angular momentum 1, spin 1/2. So if you're in the spectator with neutron as a spectator with neutron alpha pairs, this spectator interacting with this pair must also be in p wave and spin 1/2 because it's a neutron. So if you couple this, you have a total angular momentum 0, total spin 0, or total angular momentum 1, spin 1. But in the other spectator representation, because this pair is a spin singlet, so it's S0, L equals 0, this spectator is a spinless alpha particles, right? So it must also be in angular momentum 0, spin 0. So you couple to total L equals 0, total S equals 0. So this will all give you the final total J equals 0 with parity plus. Okay, so we use that. I think I'll just skip some details here. So here if people have find that if our S wave case, if A0 and R0 are all in this low momentum scales, then you can actually use some resummation of high order interactions. So you can use the square root of momentum dependence to write down your potentials. But also in P wave, because we have A1 and R1 both at leading orders, so you can also use the same strategy by resummation of C2 and C4 and write it into the square root momentum dependence form. So what happens is that after you do that, the on-shell T matrix will stay the same. It's same as what you can find in the scattering results. But the off-shell part of the T matrix will be changed. It will change into this form. And the good thing about this form is that for the off-shell part, this denominator does not have this spurious deep state pole anymore, deep state bound state pole anymore. So actually, for this off-shell T matrix is what really matters when you solve bound state problems. So the bound state pole is removed in this new power counting or unconventional N alpha interactions. So after do that, we can solve the 3-body problems for helium-6 and plot its binding. So first of all, you put 3-body force at 0, so you see the same behavior as Thomas collapse, right? So you find ground states grow up with a cutoff and find another excited states will keep growing. But here, once you put the 3-body force in and turn the binding energy to this 0.97 MeV, so you'll find that once you keep growing your cutoff, the 3-body force will have this log oscillation behaviors. But you can also find that if you are on this branch, on this dash line, at certain points, you cannot fix your ground states to this 0.97 anymore. You have to pick the excited state to fix to the excited state to the true 2 neutron separation energies. So this is also where the new excited states will happen to jump in. So you can compare these two pictures. Okay. So by doing that, we also calculated the energy dependent, the cutoff dependence of the amplitudes, and find that once you do this unconventional power countings, it converges faster than the traditional way. So I think I don't have enough, and I think it's a lot of details. So you can, if you're interested, you can go to some these papers to look at it. And I think I will use maybe 5 minutes to explain what we did recently about alpha clusterings. So this is a beryllium 9 systems, 2 alpha plus neutron forming a bromium systems. And so this is actually very important for our processes, nuclear synthesis in the neutron-rich environment, because the formation of beryllium 9 will have two processes. One is a sequential way. First 2 alpha form a beryllium 8, then absorb and capture another neutron formed into beryllium 9. Or we have a direct process of alpha neutron formed into beryllium 9. So actually, this is very important. These two mechanisms is very important to explain the reaction rates in the fusion mechanism. Because if you in the astrophysical environment, if you plot it at the temperature, the the reaction rate is very sensitive to the temperature. So if you pick a different mechanisms, it's a correlation with the temperature is very different. So this is important to understand which will be the dominant mechanism. So we try to do this because in experiments it's difficult to directly measure this fusion reactions. But what you can do is to do a reverse process. You measure its photo disintegration, which means you use a laser to shoot the beryllium-9 and cause it to excite and break up into alpha or alpha neutron components. So this has been done in I think it's done in this Higgs lab in I think it's at Duke, right? It's so they can measure these different channels, and this is representation of this transition from. So the ground state is 3½ minus. So you have an E1 transition go to 1½ plus. So and you can find the different measurements will have some quite different results. So what we are trying to do is you embed this halo EFT type interactions into a three-body calculations using hyperspherical harmonics method combined with Lorentz integral transform. I think the details is, I will skip the details just to mention that in the hyperspherical harmonics expansions, you increase your model space, your ground state binding energy will then converge to stable numbers. And then you can use the inverse, this Lorentz integral transform method to try to calculate this E1 strength and also calculate the photoabsorption cross section. So here is representing this E1 transition from ground state to 1½ plus state. So we show that if it has a weak cutoff dependence, as this green line and the dark line, and agrees relatively well with the data. And you can also add other channels. Under this E1 transition, it can also go to 3½ plus states and 5½ plus states. So you combine this would show 3 different channels. You have this green line representing the combination of these 3 channels. So they will give you these 2 peaks measured in the experiments, but once the energies go to larger regions, we have an overestimate of this reaction rate. This might be due to we only doing leading order calculations. Maybe if we include high order interactions, it might suppress the rate at higher at higher energies. And also we make a comparison with. So this is using Seeger theorems, which means you have using continuity equations, partial rho, partial t plus delta dot j equals 0, right? So this is the continuity equations. So which means that if you transfer it into momentum space, you have transfer energy times rho plus q dot j equals 0. So you can write a current operators into a density operators. And this, by doing that, you can absorb those 2-body currents into the density operators. This will be an easy way to do these calculations. So we actually, this calculation is done by using the Seeger theorem. But if you don't use that, just plug in the 1-body current, you will find that you will get this blue line. So it will have a large discrepancy from the green line, which means the 2-body current is very important in this case. Okay, I think that's okay. One more is that besides that, we can also have Hoy states. We talked about this before. Is that it has not only strong interaction but also have Coulomb. So it's interesting because you have both Asimov attractions and Coulomb repulsions. So there might be some resonance regions in the middle that can help you to form this 0+ resonance states. So, and I think this can be an interesting topic and to try to understand it from Asimov physics. Okay, I think that's it. That's all the slides I want to show. Thank you.
Thank you very much for the nice talk. Okay, so now in the paper is discussion time, and you have some question. No, you don't have. Oh.
I have two questions. Like the first one, that was when you spoke about like a FM of physics in Triton. I
Triton,
think there was this plot like with the binding momentum with as a function of the scattering length.
The scattering length.
You know,
Triton?
like, yeah, Triton. Like the scattering length is fixed, and then
Okay. Let me see if I. This
yeah,
one?
that one.
Yeah.
So the scattering length is fixed, so you get on this line, and then like the deuteron, like you know the binding energy, so you know the binding momentum. The Triton the same, but like
Right.
how do you go from let's say the two red points, so that's for the ground state, but like to get the excited states, like how do you move to the left? Like how do you get the excited state from the
To the left?
like
You cannot not move to the left because left means your two-body scattering length will be this is a triplet, right? Triplet scattering length will be negative. In nature, this is a fixed number, right?
Okay.
But in atomic physics systems, you can change this.
And then like on this plot, like where do you see an excited state? Like
Well, if in
Triton.
case if we are lucky, we can suppose the triplet scattering length is larger, then this line can move closer inside.
Okay.
So then at certain points, then the excited state will emerge. But unfortunately, this does not happen in nuclear physics. Because actually, most of the time in nuclear physics, you have ROV, the expansion parameter is about 1/3. I think this also happens in chiral interaction, chiral forces. We only have expansion parameters of 1/3. It's not like atomic system. You have the factor can be 1/20 or even larger.
Then I had another question for, at a certain point, like you show like the STM equations, and at some point you did like these S-wave projection, right? If you do like let's say a P-wave projection, so that means like there were like a, like tri-dimensional integral, and you go to a one-dimensional integral.
Right.
Like if you do like a P-wave projection, that means you will end up like with the two-dimensional integral, like you will have to leave an angle, right?
Still, you integrate out all the angles, so still end up with only the one-dimensional integrals.
Okay.
So this is so it's let me see. Okay, I don't have the formulas, but it's all the angular. So you first figure out all the angular momentums, and you just do partial wave projections. But once you do this permutation, you change from one frame to the other, they will have some angular momentum coupling, and also when you switch the frame, there'll be some angular momentum reshuffle. And this is it's more complicated than S-wave case, because if you just have S-wave, then it does not change much. But if you have other angular momentum, this becomes complicated. But it's explained in either Glaucus book or in some other few body physics book. It will give you, it's related, finally related to some 6J symbol and 9J symbols. It just tell you how you do permutation from one frame to the other.
Maybe like a short last, like at some point, like in the STM, like you add like the three-body force, like and you limit like the cycle behavior, and then you do this integration, like to check if like like this cutoff dependence, you want to remove the cutoff dependence,
right?
And then there was like this H lambda plus 1/q squared, like in a like the 1 over like the three-body stuff. I thought that was
here, right?
Yeah. But there was another point, another equation was there was like, when you want to limit the cycle, you just integrate like the three-body part, like the H lambda over lambda square, and then there was like a 1/q square.
Okay. I think I talk about the S-wave.
Yeah,
this
that one.
Right.
But like the first term, like what is that actually?
This is related to, related to here. Because you're integrate, you just look at the cutoff dependence, right? So you just put Q to quite large numbers. So you can remove this B3 here, and so you So Q is small, right? So Q prime is large. So you can make a Taylor expansion of this log term. This will turn to this 1 over Q prime square. And it's also, you still have this part, right? So you need to compare this to make sure the cutoff dependency is cancelled.
Okay. So any other question? Okay, so I have a question.
Yeah.
And so at the end of your talk, and so carbon 12 is one of the good candidate for the some an hemostat, right? You are interested in. And the same analogy, how is the for the hemostat? And you are, how is your opinion? Because you are just focus on the 3-body hemostat, right? And now, for instance, in the case of the helium-4 bosonic system, also we have a 2-bond state for the helium-4 tetramer state, right? Yeah, so then, of course, in the case, if we go to the helium-4 bosonic state, maybe so the if we focus on just excited state, maybe hemostat. The same analogy in the nuclear physics, do you have any opinion for the 4-body hemostat, something like that?
4-body hemostat. Well, I think there's not that much possibilities because helium-4 doesn't have it, right? But if you think about tetraneutron or multineutron systems, the difference is that it has spin, right? So it's at Pauli forbidden. If you have more neutrons, those neutrons need to go to P wave. And then the picture will be different from ephemeral pictures for the boson systems.
The same analogy, how about oxygen-16? It's a
Okay.
kind of bosonic state because if so you have some find the hemostat for the in the carbon 12, it's a 3 alpha, right? Maybe
Right.
you would just focus on just excited state for the 0 state.
Yeah.
The same analogy, maybe oxygen-16, how is it?
Yeah, I think oxygen-16 also have a like Hall state. And
Okay.
people have studied this alpha condensation in this oxygen-16 and even beyond that, right? So it's, I think you can find those alpha clustering, but maybe not in the ground state.
No,
So
just
in the,
excited
excited
state,
states,
yeah.
yes, there are many things to look at.
Okay, yeah, quite interesting. Okay, any other question? Okay, maybe if not, you
It's
must be so
lunchtime,
hungry.
yeah.
So then let's finish. So the Professor Chen's talk. Thank you very much for the nice
Yeah,
talk.
thank you.
Okay, and next session will be start at 1:30, right? Yes. Yes, just so in lunchtime.